and I are excited to share about the work that mostly Thuan has done for mapping oil palm using Earth Engine. So basically some background also towards the project. This is something that I have worked before on using an earlier version of Earth Engine in 2013, but at that time it wasn't so easy to access radar imagery on Earth Engine. And when Thuan came along, I think in 2017, he was an exchange student from Hohenheim University in Germany to Nanyang Technological University in Singapore. He decided to develop his master's thesis on this project. So this is an output from his master's thesis and after about 8 months of work using Earth Engine. So I'll just begin, and Thuan will carry on with presenting more about what and how he did the coding in Earth Engine. All right, so maybe just some introduction, which for those of you who are unfamiliar with the topic of oil palm oil is a very lucrative and also a widely used vegetable oil in across the world in all sorts of products. And it has got lots of benefits and costs to it. So the benefits of it is that it is a very efficient land use edible vegetable oil, which has got very efficient land use. It has got a high price for farmers, and it is a crop that can grow very well in the tropics. But that is also the problem because it competes for land in the tropics, and especially in Southeast Asia, where we have large swaths of forests that have been affected by the expansion of palm oil, especially in the last 2 to 3 decades. Indonesia and Malaysia has been mostly hit by this expansion. And I think this encroachment to oil palm is also increasing even up north in Myanmar, where one of the users or audience here has also mentioned is studying land cover change in Myanmar. So these are some of the costs and benefits to palm oil, and this is why we are looking into monitoring palm oil plantations and using Earth Engine as a tool for doing large-scale mapping of oil palm in a rather rapid manner. So there has been a lot of studies that have looked into the mapping of oil palm, monitoring of oil palm, and with the onset or this development of Earth Engine as a tool, it's been explored to map out oil palm plantations as well. Ours is really not the first study. There have been many other studies that have looked into mapping oil palm. Keiko Nomura has published one in Myanmar. There was one recent one by Descals in Indonesia, looking at also radar and optical imagery for mapping smallholder and industrial scale oil palm. And one of the inspiration that also sort of like spurred us to look into this was a colleague of ours in National University of Singapore, Don Dialban, who used combined radar and optical satellite imagery to look into oil palm or in general land cover expansion in Myanmar. So this was something that also caught my interest, and this was something that Thuan was also interested to look into. So we are interested to see, whether or not the fusion of these data sets would yield higher accuracies rather than just using optical or radar imagery alone. So our first question was really to test, whether the use of the combined images, radar and optical imagery for oil palm classification will outperform radar only or optical only classification. And our second question was to look into this automated map of oil palm plantations and compare it with 2 other independently sourced oil palm extent maps. One is a 250-meter automated map, and another is a 30-meter digitized map of oil palm plantations for the same year. So for this, we looked into the 3 provinces of Sumatra, Riau, Jambi, and South Sumatra, which has got very high extents of oil palm. And I'll let Thuan elaborate more about how the methods of looking into Earth Engine for mapping oil palm from here.
Yeah, I admit it's fine. Yeah, thanks. Thanks for the introduction, Janice. Yeah, so we chose the 3 provinces in South Sumatra, in Indonesia, because they were the most covered by oil palm, like Riau and Jambi and South Sumatra. And then from this, we did some pre-processing. On the next slide, you can see the pre-processing we did on the imageries. So we use two kind of imageries, Landsat and radar imageries. And for the Landsat, we did a compositing, a pixel-based compositing. So we chose the best pixel for the year 2015 on all this area, on the area of those 3 provinces. And for the radar imageries, we use the pulsar imageries from like provided by the Japanese government. And we did a speckle filtering and a normalization of the data. So you can see on the pictures, the gray, it's 4 gray pictures. So you have one which is filtered, which is a bit smoother than the one which is not filtered on the right. And then from those 2 data sets, we calculated some indices. So for the radar, we had the radar indices and also texture measures. So texture measures are like a value which depends on how pixels are organized on a 3 to 3 squares. So it gives some indication about the organization, the relative organization of the pixel in a window of 3 to 3 pixels, so 9 pixels. And for the Landsat, we also calculated some vegetation indices like NDVI, EVI, and from all those indices, we could run then a random forest, so a machine learning algorithm, which classified the pixels to some classes that we have on the next slides. Yeah, so 6 classes, land cover classes. The forest, which was defined as a homogeneous area covered by trees. Then we had the forest shrub mosaic, which was more like an heterogeneous area with like shrubs and trees. And then we had oil palm, which was mainly plantation, industrial plantation of oil palm, like you can see here. And the water, the rivers, also the lakes, and then build-up areas, mainly cities, roads, towns, industrial areas, and the background crop, which was like any background which was not oil palm. Yeah. And we sampled those, like you can see the red squares. So they are like samples of land cover classes. And we sampled about 0 to 4 samples per regencies for all the provinces. And so when there were a lot of water, for example, we could sample 4 samples of water. But in some regencies, there was like maybe 1 lake, or there were no water, so we couldn't sample any water for this regency. So it gave a total of 788 polygons, like you see on the image. And those, like, for example, for the forest, there were 140 polygons, for water, 117. So it was unbalanced. And we also tried to have more polygons, more samples for land covers, which were more difficult to classify, more diverse. And also for oil palm, we tried to have many samples because we were interested in oil palm. And then from this, we randomly selected a pixel in each of those polygons. And then we use those pixels as training pixels or testing pixels. So you can see on the small table on the right. At the end, we had like about 200,000 training pixels for the radar classification, and 730,000 for the Landsat, and 130,000 for the combined classification. So we did 3 classification: one with only the radar imagery, one with only the Landsat imageries, and one with the 2 together. And the idea was that when we combine the 2 Landsats, to the data sets, when you combine the 2 data sets, we get a better classification. I think we see it on the next slide. Yep. So on the 6th slide, we can see the difference of classification, like the result. And you can see that the radar classification tends to overestimate the amount of oil palm. I think on this area, it's because it's a coastal area and there are like some other kind of palms which are confounded with oil palm in this area. And for the Landsat classification, they tend to underestimate oil palm. So, like for example, here's a forest shrub mosaic take on some oil palm areas. And the combined area was the best classification because it had the best overall accuracy, 0.84, which was better than the two other ones. And from the combined classification, we estimated an overall oil palm cover for these three provinces altogether. And we compared it to the two other classification we had. So we had the Mittinen data and also Austin data. And those two classifications had their own estimation for oil palm. And so our classification with the combined two data sets gave a higher estimation than the two other classification, Mittinen and Austin, right? And our classification was also gave a higher estimation than the tree crop statistics, the official statistics from the Indonesian government. So I think for Mittinen was mainly because Mittinen used a very large area to do the estimation of oil palm, and also Mittinen didn't focus on oil palm but more on vegetation types. So they had a very large scope of interest. That's why they had a low estimation of oil palm. And for Austin, I think they one of the problem of Austin was the resolution. I think the resolution was lower than the resolution we used. So that's why they have a lower estimation. And I think I'm pretty happy with our estimation because it's very close to the official Indonesian estimation. So this was pretty good. And then on the next slide, we compare the errors, right? And we see that for the Landsat, for example, most of the errors are from for oil palm are from the forest shrub mosaic and forest, because Landsat is based on light, on what we see, and usually forests are green and oil palm are also green. So the algorithm tended to confound the two green land covers, the three green land covers: forest shrub mosaic, forest, and oil palm. For the radar, the problem with radar is that the radar is based more on sound waves, and those waves are reflected by the vegetation and by the ground, buildings, and the way they are reflected by the ground is similar in all the different land covers which have a ground, like a dirt, right? And because it's a very specific way of reflecting the waves and the sound, so the oil palm was confounded with other land covers which had some ground on them, like forest shrub mosaic and also the bare ground crop, I think. Yeah. And for the combine, which was the best classification, there was a bit of errors on bare ground crop and forest shrub mosaic, confounded with oil palm. Yeah, but it was lower than the two other classification. Yeah, and then we did the comparison of the areas of agreement between the classification, like our classification, and the two other classification from two other group of researchers, like Mittinen and Austin. And we overlap the maps. For example, on the A, like the one on the left, we overlap the combined map with I think this one is a Mittinen. So on the A, we compared the Mittinen and the combined maps we did. And this gave us area of agreement where there was no oil palm in black, area of agreement where there was oil palm in yellow, and area of disagreement where either the combined map detected oil palm while the reference map didn't see any oil palm, so that's a blue area. And in pink, that's the other way, when the reference map, like the Mittinen map, detected the oil palm and the combined map didn't, right? And for the B, the map on the right, it's the same, but with the Austin map. So the combined map plus Austin. And if you would see the difference between the two comparison, we can see that the Austin map had more area of disagreement with the combined map, and those area of agreement were mainly like with Austin map saying that there was oil palm and the combined map saying there was no oil palm, right? So that the pink areas. And to have a better idea of how similar were the maps, we calculated two indices, so the Jacquard index and the Kappa index for each of those two comparisons. So for the combined in Mittinen, the Jacquard index was 0.55, and for combined Austin was 0.40. So it means that the combined in Mittinen were more similar together than combined in Austin, right? Because Jacquard index is like an index which calculates the overlap, like how much two maps overlap together. And the Kappa index is also a similarity index, which compares more like how the overlapping which happened between those two maps, how this overlapping is due either to chance or really to similarities, right? And here again, the Kappa index is higher for combined and Mittinen than combined and Austin. Here. And then in the next slide, we wanted to see more in detail where who was right for oil palm, like which map was right and which one was really detecting oil palm was there were oil palm and which one was missing oil palm was there were oil palm on the ground. So from the comparison map that we saw earlier on the previous slide, we randomly selected 100 points somewhere on this map, randomly selected through GIS. And then we visually checked what was the land cover which was detected on this point in 2015. So then we, in an Excel table, we said whether the Austin map was right or either the combined map was right, or for the Mittinen combined, if the combined was right or the Mittinen, right? So, for example, on the left, we can see that from the 100 points we randomly selected, about 70% of the points which said there were oil palm on the ground. So 70% were rightly detecting oil palm in both combined and Mittinen, right? So it means that both maps were equally good at detecting oil palm in this time in 2015 with our methods. And for Austin, then the combined map had a higher rate of oil palm, like percentage of detected oil palm, like was like 65. And for Austin, it was only 27, 28. So it means that the combined map was better to detect oil palm than the Austin map for this data, like according to this data, right? But then it's also very important to check the methods they use to detect oil palm in what they use, what the scope of the study. And for Austin, they use mainly visual detection. So they took some Landsat imageries and they looked at the imageries and they drew manually the different plantations, right? And for Mittinen, they use the automated method with an algorithm which classified like all the land covers and then grouped them in a certain number of vegetation types, right? And like those two differences in like performance, I could say, between Austin combined and Mittinen combined. So at the beginning, I thought the combined was better than the Austin because the performance was higher, like 60% against 28. But I think at the end it's just a reflection of how the methods are different to detect oil palm. And this table shows us more than the combined method we used is closer to the Mittinen automated method they used to classify oil palm. It's closer than the Austin method because Austin was manual and visual. And our method with the combined data sets was more semi-automated because we ran a random forest, and this is similar to what Mitinen did in a way. And those classifications are similar in methods, so they give the same performance, right? And Austin, which is a bit different, gave a different performance, like a lower performance. It looks like it's lower, but I think in the end, in the conclusion, we concluded that it's good to have both visual and automated detection, like way of detecting all time. I think Janice can finish on with the conclusion, right?
Okay, yeah, great. Yeah, thanks very much, Thuan. So like what Thuan had mentioned, what we were first looking for was to compare the accuracy of the combined with the radar and also the optical imagery. And I think we showed that it's always better to have both images to be able to detect oil palm. And then for our approach and comparing that with the Mittenen's land cover product along with Austin's land cover product, as what Thuan had also mentioned, it's very much a reflection of the different approaches that are being used. One good way of, Austin's approach was visual detection and digitizing of these oil palm plantations. And so she could use a lot of the land use features which might not be something that is picked up by the automated method. So for example, some of the oil palm plantations might be immature or diseased, but they do still show the grid-like pattern of oil palm plantations that you can see from satellite images, and those would have been included by Austin and considered as oil palm plantations. Whereas for our approach, it's very much looking at a random forest classifier to try to tease out whether or not that pixel is part of oil palm or not. So I think it's just a reflection of the different approaches. And there was also a paper that compared the automated and the visual approaches from Mittenen and David Gavu's work in 2018. So that's something that we also concur with their conclusion in terms of a need to be cautious when you're using automated approaches for detecting oil palm. So I think with that, we end our presentation. And Sabrina, you could take over for the moderation.